In 2022, machine learning engineers encountered a plateau in model scaling. While doubling parameters improved general capabilities, it consistently failed to improve performance on multi-step logic. This chart plots accuracy against parameter scale for a dataset of grade school math problems called GSM-8K. Under standard prompting, that red line is aggressively flat. Even as the model grows significantly larger, there is virtually zero performance gain. The failure is mechanical. Standard few-shot prompting forces the model to jump instantly from a question to a final answer. It provides no intermediate computational space to work through the logic. To solve this, researchers initially looked towards rationale-augmented fine-tuning, teaching the model to produce its own intermediate steps, but the cost was high. It required running entirely new, task-specific training cycles on massive datasets of human-annotated rationales. Improving reasoning meant paying for a fresh training run. In 2022, a team at Google Brain published Chain of Thought Prompting. They achieved state-of-the-art reasoning results by changing the prompt text alone, leaving the language model's weights completely frozen. This represents a move from expensive model training to pure prompt engineering. However, the data reveals that this capability is tied to a strict gate based on model scale. The chain of thought intervention is strictly an exercise in string manipulation. There are no weight updates and no architectural changes to the underlying model. We can formalize this context using a prompt construction operator. P of Q is the final prompt. It's a concatenation of several few-shot exemplars, the test question, and the final trigger, A. The only controlled variable in the system is the injection of a reasoning chain into the output block. A standard exemplar moves straight from question to answer. The chain of thought exemplar forces the text to pause, inserting a series of natural language steps before the final result. Once the prompt is built, the frozen model executes token-by-token greedy decoding at zero temperature. It produces a single deterministic response. The resulting text then hits the answer extractor, the most fragile component of the engineering pipeline. Lacking a structural output format, the extractor uses a rigid code logic. It must parse the last match of the terminal phrase, "the answer is X," to calculate accuracy. This creates a specific parsing risk. If a model outputs a stray phrase like "the answer is" in the middle of its logic, it can trigger a normalization failure. The system will record a 0 for accuracy, even if the reasoning was sound. Because chain of thought relies on a frozen model, its success is a brittle pipeline. It depends entirely on the model honoring a strict text template. Asking a model to show its work is not a universal benefit. The performance gain is deeply dependent on parameter count. This relationship is measured by the chain of thought gain metric, or delta, which is the accuracy of COT prompting minus the accuracy of standard prompting. This graph charts that delta. The flat red line is the standard prompting baseline. At scales below 10 billion parameters, the blue chain of thought curve actually dips below the baseline. Accuracy only shifts into a steep, nonlinear gain once the model crosses the 100 billion parameter mark. This raises a mechanical question. Why does forcing a small language model to think step by step degrade its performance? The researchers found that smaller models produce fluent but illogical chains. They confidently output incorrect derivations that sound plausible. A small model has enough language fluency to make each individual sentence sound right. What it lacks is the parameter capacity to sustain logical state tracking across multiple steps. Local connections work, but the global logic derails. Chain of thought does not generate reasoning where none existed. It merely provides a format for latent reasoning to occur, provided the model is large enough to support it. This establishes an operational reality for engineers. Deploying this strategy only works if you have the significant compute budget required to serve a frontier-scale checkpoint. What exactly causes the performance jump at scale? Is the model genuinely reasoning, or is it just mathematically benefiting from generating more tokens? To find out, the team ran 3 null hypothesis ablations, systematically removing parts of the prompt to isolate the cause of the gain. Ablation 1 forced the model to output a mathematical equation instead of natural text. The accuracy falls immediately to the baseline level. This proves that complex word problems require semantic, natural language decomposition rather than just symbolic math. Ablation 2 tested variable compute. It forced the model to output a meaningless string of dots equal to the length of a reasoning chain. Again, performance drops back to the baseline. The gain is not an artifact of giving the model more compute or extra tokens. The intermediate content must be meaningful. Ablation 3 modified the prompt so the model outputs the final answer first, followed by the reasoning chain. Performance collapses. This confirms the chain cannot just retroactively activate knowledge. It is executing causally precede the answer. The generated text acts as a vital state tracker during inference. We still have to determine if this is genuine dynamic decomposition or just a sophisticated form of pattern matching. This chart shows the results of an out-of-distribution length generalization test. Researchers gave the models 4-step logic problems after only showing them 2-step examples. Standard prompting collapses to near zero, while the chain of thought bar maintains its accuracy. Surviving this test proves the model is dynamically composing novel steps to solve longer problems, rather than memorizing fixed-length patterns. However, the error logs reveal a structural flaw. Roughly 46% of failed chains are conceptually sound, but derail due to a single arithmetic slip. By intervening with a post hoc external calculator to fix that one slip, accuracy instantly recovers by up to 4 points on benchmark datasets. These arithmetic failures define the ceiling of pure language generation. They expose the necessity for external API tools to handle execution. The work of Wei and his colleagues presents a clear trade-off, achieving state-of-the-art reasoning with zero training cost, but bounded by a significant computational gate. The largest scientific caveat is that chain of thought offers no correctness guarantees, and it leaves the question of faithfulness open. There is a critical distinction between a model outputting text that emulates a thought process and that text serving as a faithful transcript of the model's actual computational steps. Findings from 2023 showed that these chains can act as post hoc rationalizations. A model can generate logical text to justify a conclusion that was actually reached via hidden biases in the training data. Despite this limitation, chain of thought established the technical substrate for autonomous agents. You can trace a direct evolutionary path from this paper to systems like React. The discovery of arithmetic execution slips directly inspired researchers to interleave chain of thought reasoning with actual calculator tool actions. While this prompting strategy may not guarantee perfect logic, it provided the essential single-path text substrate and made complex, multi-tool AI agents possible.